Hey everyone, in this video we're going to introduce hypothesis testing. And we're going to be doing this for pretty much the rest of the semester. This unit is all about inference. And so our goal, our purpose is to figure out if an observation that we've made, so we just ended the last unit talking about sampling distributions. And we know that if we take a random sample of size n from a population, that its mean can vary from the population mean, and that's okay. What we want to know, though, is if we're trying to do something that affects change, we're doing an experiment to see if a drug is helping patients with a certain condition, we want to know whether the sample that we're taking, the mean of that sample, or the value of an individual is significant change. Or is it just chance? Did I just happen to pick somebody or a group of people where the mean varies from the population mean, but it's just because there's natural variability in any sample that I take? So what we're really looking for here is that something is statistically significant, okay? So we want to know that the difference between what we expect to get and what we actually get is not because things are normally distributed and there is naturally variability. We know that most data sets have a standard deviation. We want to make sure that chance did not cause this difference. We want it to be statistically significant enough that it's very unlikely that chance caused that to happen. So what we do is we form a hypothesis, which is basically a conjecture that something is true. So here are some examples. This drug will be better at treating cancer. This teaching technique will increase student performance. Vitamin E reduces colds and fights off other diseases. Eating too much fish will lead to higher mercury levels in your bloodstream. The Atkins diet will cause more instances of heart disease. So all of these are hypotheses. And how do we know that in the sample that we've chosen that some of the people just were able to get better from cancer just because some people have that ability? In the grand population of this world, there are some people that are better at fighting cancer. There are some students that perform better. There are some people who fight off colds and other diseases better. So how do we know that the results that we're seeing are from vitamin E, for instance, instead of the natural variability of some people to just better fight off colds and other diseases? So statistically speaking, a hypothesis is going to be a numerical value because we like to deal with numbers. And so what we will do is we will talk about a population parameter. And just to remind us about population parameters. So one population parameter that we've been using a lot is mu, and that's pronounced mu, okay? And that is the population mean. We've also talked a lot about sigma, and that is the population standard deviation. So basically, we're going to make a statistical hypothesis by looking at one of these population parameters and saying something about it. So in the case of a teaching technique that will increase student performance, we would say that mu is going to be bigger than it was historically, okay? So we actually have to form two separate statements. We break it up into two things. We have our null hypothesis, which is H naught, H sub 0, which is often called H naught. Okay. And this is the hypothesis that's going to be assumed to be true, unless we get some data that says otherwise. And so typically, this is the status quo, and it's often just what the historical mean has been. We're going to say, in the case of increased student performance, the null hypothesis would be that the mean is still what it's always been. So let's say that historically students perform, they get a 75 in a college course. The null hypothesis would be the students are still getting an average of 75. And we know this teaching technique, or somebody's claiming that this teaching technique will increase the student performance. So what that means is somebody thinks that mu is going to be greater than 75. And so this would be my h naught, and this would be my h sub a, which is my alternate. Oh, this says null. Sorry. This should be my I can't even spell. This would be my alternative or alternate hypothesis. Alternate or alternative hypothesis. This is the hypothesis that somebody has claimed, like this teaching technique will increase student performance. So we think that mu is actually greater than 75 now. So there's different types of formats that are associated with a null and alternate hypothesis. We're going to get to that soon enough. Another thing we should know about is a sample statistic. So once I make a claim that, I'm just sticking with this one here, that a teaching technique will increase student performance, we have our null hypothesis, and that is, okay, it's always been that the average for this course has been a 75. And so until you can prove otherwise, I don't think your teaching technique is doing anything. Maybe your sample of students are just higher achieving naturally in the grand scheme of chaos and randomness. You just happen to get a group of students that perform better than 75, but it's not statistically significant. And somebody says, no, I think this teaching technique really is causing students to get averages that are higher than 75. And so they have a group of students, or maybe they have several groups of students, and they've done this for 5 semesters. And in each semester, they found the average for that class. And so they have now a statistic. And for those five semesters of class size of 40, they know what the average is. So in the next lesson, we'll talk about actually how to calculate all that stuff. But for right now, all we're talking about is there's a test statistic. At some point, there will be information provided in the sample, and the researcher is going to use that to decide whether we accept the null hypothesis or choose not to reject it, or if we reject the null hypothesis and instead accept the alternative hypothesis. So that's really where we're going here. So I'm probably going to use the word alternative more than alternate. So there are 3 formats that can happen here. And the one that we just went over, that's what's called an upper-tailed or it's still a one-tailed. The first two that we're going to talk about are one-tailed. But basically, we have our H naught, where mu is equal to a number, and that's going to be some historical average. And then our alternative hypothesis is going to say mu is greater than that number. We think things have changed, and this is the reason why we think they've changed. Now let's see whether that change is significant or not. So this is called a one-tailed hypothesis, okay? And this would be specifically upper-tailed for obvious reasons, because we're greater than, we're upper. We're on the right side of where the mean used to be. We have our null hypothesis that the mean is still what it's always been. It's some number. We have our alternative hypothesis that says, you know what? I think the mean has gotten smaller. Okay. And this is also one-tailed. And this is a lower-tailed hypothesis test. Okay. And then, finally, we have our third situation where our null hypothesis, H naught, says, you know what? I think the mean is what it's always been, historically. And somebody else comes along and says, no, I think it's changed. It's just no longer that value. So this means that it could be greater than, or it could be less than. It's just going to be outside of some range, some normal range that we're used to. This is called a two-tailed hypothesis test. Now, why are these called one-tailed and two-tailed? Well, this goes back to the idea of a normal curve, right? And so if this is our population, and remember, at first at least, we're going to be taking, this is going to be a sampling distribution. We're taking a sample and we're wondering, how does it compare to the population? And it doesn't matter if the population is not normally distributed. If the sample that I'm taking is large enough, then the sampling distribution is normally distributed. And we know that the mean is what the historical mean has always been. And we're trying to prove that, hey, I think the mean is actually larger. And if it's farther enough away on the right side, this is one-tailed. This is one-tailed to the right. If it's big enough, far enough away, lower than the mean, this is a lower-tailed hypothesis test. And if I just don't care, I just want it to be a certain distance away from the mean in either direction, that's my two-tailed. You can see both tails are being highlighted. And so we are going to be using all of the stuff that we learned about probabilities and finding the probability that something happens below a certain value, especially when I'm doing a sampling distribution. And then we're going to compare that to a value that we're hoping that we set, called the level of significance, that we'll talk about in just a little bit. And that will help us determine whether we accept or reject our null hypothesis. Okay? So, here's our first example. Any Boston Celtics fan or rival knows that Shaquille O'Neal was not very good at throwing free throws. Over the course of his career, his overall made free throw percentage is 53.3%. So during an off season, Shaq was working with an assistant coach on his free throw technique. Pretend we're back in the day when Shaquille O'Neal was actually playing basketball. During an interview, the assistant coach claimed that Shaq's free throw percentage had improved dramatically. So here's a claim. We have a historical number here, and now there's a claim that his free throw technique or percentage had improved dramatically. So we want to specify a null and alternative hypothesis for what the assistant coach has claimed. So the null hypothesis is going to be that Shaq is still going to be shooting 53.3% of his free throws and making them in. The alternative hypothesis, and the reason I'm choosing this as my null hypothesis is because this is the way it's always been. We're comparing him now, after going through this miraculous free throw technique training, to what he was before. So I'm not convinced. I think, you know what? He's still the same old Shaq. And maybe some of the free throws he's making right now are just part of the normal fluctuation of free throws that a player makes and doesn't make throughout their career, that all even out in the end and are actually normally distributed. The alternative hypothesis here is that no, you know what? His free throws, his free throw percentage did actually increase, and the mean has changed. And this is a significant change. It's so much that the probability that the change would be this high above the mean historically is so low that since the probability is so low that this happened, then we can only attribute this to the free throw technique that he's been working on over the offseason. And it's not just because of statistical variance and variability. All right, so now here's another example. So a new possible work of William Shakespeare was discovered in an Oxford library. The person who made the discovery is convinced that this work is truly Shakespeare's. Critics claim that this is the work of a forger. Previous knowledge of the works of Shakespeare show that on average he used 8.2 new words for a new poem of this length. Specify a null and alternative hypothesis for a test of the critics' claims. Okay? So again, you find this work, this poem, it's signed William Shakespeare. To anybody, and it's from the right time era, it was preserved. So to the observer, I would say, the person who discovered this, they think that, you know what? This is William Shakespeare, so his average is probably going to be about 8.2 new words for this poem. All right? Now, if the actual new words for this new poem are more or less than that, does that mean it wasn't Shakespeare? No, because Shakespeare himself is human and is variable and complex. And so it's possible that the number of new words in this poem are more than they normally were, or they're less than they normally were. But is it statistically significant is the question. And in this case, we don't care if it's more or less. We just want to know, was there a change? Okay? So this is an upper-tailed hypothesis test, and this one is a two-tailed. And it is important to know the difference because when we start talking about the outcomes and what could happen and the probability that we got it wrong, then it's really important to know whether or not it's a one-tailed or two-tailed, because the way that we calculate and use alpha changes. Okay? So there are 4 possible outcomes. Think about a trial, right? So somebody's on trial for murder, and if you convict them, they will go to jail for the rest of their life, or they will be sentenced to death. Okay? The first outcome could be that, it's called a type A decision, that in reality, the person was innocent, and we concluded that they are innocent. And notice how we're talking about a court case, and somebody is presumed to be innocent. That is H naught. would be that somebody is innocent. Somebody is innocent until they're proven guilty. So H naught would be that somebody is innocent, and then guilty would be an alternative hypothesis, which would just be not innocent. Okay? So, in reality, which we can never know what the actual truth is, that's why we're doing this, because we don't know the truth. We can get this wrong. It happens all the time. We don't know when it happens, but the probability suggests that it happens. Okay? So in reality, which we can't know, it turns out that this person was innocent and we said they were not guilty, which is good. That's like best outcome, right? A type 1 error is that the person was innocent, but we decide to reject H naught, meaning we decide to accept. It's not really accepting the alternative hypothesis. We are just no longer accepting the null hypothesis. Okay? So what always has been true, now we don't think is true anymore. Now this is bad, right? This is called a type 1 error. And the probability that a type 1 error happens is called alpha. And this alpha number is called the level of significance. Okay? So this is the case where somebody was actually innocent and we convicted them of a crime. That's not great. Type B decision is that the alternative hypothesis is true and we concluded to reject the null hypothesis. So this is somebody was actually guilty and we said they're guilty. So that's also a good situation. A type 2 error is that somebody is guilty, but we say, no, we're going to stick with the null hypothesis and say that they're innocent. So we just set a guilty person free. Now, which of these is worse? This is a type 2 error and is denoted by beta. So this is an alpha, this is beta. So a type 2 error, the probability that a type 2 error happens is beta. I think it's much worse to put an innocent person behind bars than it is to set a guilty person free. And that's what our whole justice system is built on, or at least supposedly it's built on. So it turns out that alpha and beta are linked together. They're actually inversely proportional. So the smaller I make alpha, the larger that beta gets. So I can make sure that I am 100% certain I could make alpha as small as possible. The probability that I take an innocent person and put them behind bars, I make that as small as possible. And what happens is more guilty people go free. Okay? So I don't always want to make alpha too small. And so the accepted values for alpha are typically 0.01, which means there's a 1% chance that I convict somebody who was innocent, which I don't think our court system's based off of it so that it's 1 out of 100 times. I think it's much less than that. At least I would hope so. But even talking about any of these other studies that we do with like drug studies, we want to make really certain that we're not accidentally claiming that a drug can do something that it can't do. So we would want to make this alpha really small. So alpha is either negative or 0.01. Alpha would be like a 5%, or on the high end, we would say, depending on the situation, we could say like, 1 out of 10 times we're okay with perhaps being wrong. So these alpha values are really probabilities, right? And so if the probability that this alternative hypothesis is less than the probability that we're making a mistake, then we're going to say, you know what? We're going to reject this null hypothesis, and we're going to go with our alternative hypothesis. And we'll talk a lot more about that next class. We're going to do all the number crunching, okay? So what I want to talk about now is I want to talk a little bit more about this type 1 and type 2 error. So in the context of the Shaq situation, we want to describe a type 1 and a type 2 error. So we said that the null hypothesis for Shaq was that his free throws were still going to be, what was the percentage, 53.3. And the alternative hypothesis was that it was actually going to be greater than 53.3, okay? So type 1 error would be if the, if Shaq was actually throwing free throws at the same percentage, we just happened to get a bum sample that happened to be a little bit above his, a little bit above normal, so much so that we reject the fact that he's still throwing free throws like normal. So in this case, this doesn't really hurt anybody, but basically we think Shaq is better at free throws, but he's not. So what could possibly go wrong here? Well, the worst thing that happens is people pay him more money to go to their club, to go to a different team because his free throws are getting that much better. And then, you know what? They weren't actually better. So the worst case scenario is people throw away money, which happens every day anyway. If we were doing a type 2 error, what are we talking about? In this case, we're saying that, you know what? This technique to improve his free throws, this technique works, but we don't believe it. So in this situation, everyone thinks that Shaq is still a bad free throw shooter, and the person who was coaching him, even though he had a technique that actually works, doesn't get the credit for fixing his free throws. Again, this is a very superficial problem. Nobody really cares one way or another. Okay? So we look at another example here where we have, in any tissue sample, a certain number of white blood cells will be present. This number varies from person to person, what's considered a normal range. When the average number of white blood cells in a sample falls below this range, it can be an indication of a serious medical condition. So, this is a bit of a conundrum, okay? Because we want to typically set our null hypothesis to be the better of the two situations. So I do not want to convict an innocent person. I also don't want to let a guilty person go free, but I'd rather not convict an innocent person than let a guilty person go free. Here, I would rather tell someone they're sick and try to treat them than miss the diagnosis and have them die from it. So I would prefer the null hypothesis to be that this person is sick, but the way this problem is worded makes that very difficult because they say we have a normal range and now we want the white blood cells, the number of white blood cells are going to fall below this range. This really sets itself up for the null hypothesis being that mu is the normal average, right? And the alternative is that it's fallen below the normal average. And this is white blood cells we're talking about. Now, in the context of this problem, a type 1 and a type 2 error, this is a little bit more serious, okay? A type 1 error would be that we say, so typically, again, the type 1 error is that the null hypothesis is true. Oh, actually, I guess we're okay here. We say, oh no, yeah, we say the person is sick, but they are not. So what we're saying is we think that this person has white blood cell count that's below normal, right? Because a type 1 error, the null hypothesis is true, but we reject it. So in this case, we say that the person is sick. We think their blood count level is way below normal, but it turns out that they're not. So it's not as bad of a conundrum as I was anticipating earlier. This is actually a really good situation here. It's not great to tell somebody they're sick when they're not, but it's way better to tell them they're sick and then find out later that they're not sick than to tell someone they're not sick and then they're dead later. Okay? So we say the person is sick, but they are not. That's a type 1 error. A type 2 error is we say the person is healthy when they are sick. Okay, this is worse. But again, our level of significance, we can set this one. We set alpha, okay? So the probability that somebody is sick, oh, so I guess this is the bad thing, okay? Because we would rather, we would say the person's sick, but they're not. When that happens, we would want to keep that as, we wouldn't mind that being a little bit bigger so that this wouldn't happen. If we say the person's healthy when they are sick, that's bad. And so we would want this probability, beta, to be smaller than alpha. But we don't get to set beta. Beta and alpha are inversely proportional, but we don't know what beta is. We just don't know that value. We don't have enough information for it. We have enough, we can control alpha because we know what the original data is telling us. Beta is about the new data that's coming in. And so we don't know as much about that. All we know is that we can make alpha as small as possible. But the smaller I make alpha, the more beta becomes. And so in this case, again, I was right when we first read the problem and then I confused myself. The type 1 problem, we want the null hypothesis to be the thing that we hope. So we hope we want to accuse somebody to be innocent because we'd rather let somebody who's guilty go as innocent. Okay? So in this case, I'd rather tell someone they're sick. So I'd rather make the null hypothesis that somebody is sick. But the way this was worded and the way that we do this statistically, that makes that very hard to do. All right? So how does this work, this level of significance? And I'm just going to do a quick preview of what we're going to talk about next class, and then I'm going to leave you alone. If we have a normal curve, okay? Now let's say this is something we have to set ahead of time. It is unethical to run your experiment, gather your data, find what your p-value is, which we'll talk about next time, and then set alpha after, because p is going to be compared to alpha. So p is the thing we're looking for. You need to set your alpha ahead of time. You need to say, you know what? I want to make sure that I'm only wrong 1% of the time, or 5% of the time, or 10% of the time. Or you can pick any percentage. It doesn't matter. And so what this means is for a one-tailed hypothesis test situation, what we're going to do is, let's say it's an upper, and we say we only want to be wrong 1% of the time. So that means I would just, if this is mu, this is a population mean, I know that 1% of the population is up here. So this area would be 0.01, okay, which is a very small area. Then I'm going to collect some data. And let's say I find a sample from this population, and its mean is here. The probability of the mean being here is going to be bigger than the probability that I've set out as my threshold. If my mean of my population is up here, then the probability of this happening is going to be less than this. So the probability of any of these outcomes is called the p-value. And if the p-value ends up being less than alpha, then we reject the null hypothesis. So if the value gets inside of this rejection region, then we reject the null hypothesis. But we hardly have to know like what this value is because of the way the percentages work out. The other thing, what would happen, another instance, is if we had the tail on the other side, it'd be the same situation. We'd put all 0.1 there. But if we had a two-tailed test, and mu is here, so we want to do this with a level of significance of 0.01, what we would do for a two-tailed test is we would actually take the 0.01 and divide it by 2, and so then we'd have an area of 0.005 here and an area of 0.005 there. And now we're looking for a p-value that's somewhere along this curve. If it ends up in either of these regions, then we reject the null hypothesis. If it ends up in any of this area here, then we fail to reject the null hypothesis. It doesn't mean that we think the null hypothesis is true. It's just we're not going to reject it. All right, so there is a problem set that is posted, and let me know if you have questions.